Not second, is the third chapter. So in the syllabus, what we have is blood total. Just a minute. Let me see where it is original public. So we have now syllabus mainly alpha decay, beta decay, gamma decay or gamma emission. Nothing for radioactivity in general is in the syllabus, though it is named radioactivity. So we'll begin with the alpha decay. So tell me, what do you mean by alpha particles? What do you know about them? Yes, anything about alpha decay that you know?
Sir,
Go ahead.
we have
What do you know about alpha decay?
electrons per
Sorry.
that's particles are electrons injected and not particles positive part.
You just type. I can't hear you. There's some problem in network. I hope. Just type out. Just type. I'll see. Positively charged particles. So how much positive it is? How many units of positive charge? One or two? It is chemically the helium nuclei, right? Anyways, so those things are very rudimentary. You know it. So we'll begin first by determining the velocity of alpha particles. Okay. Now this thing can be done by using a magnetic spectrograph. I told you last semester also during DSC, the first chapter, that magnetic fields can be used to project the accelerated particles in one particular direction or desired direction. That is, we use focusing. Just a minute. So here the focusing would be semicircular focusing. Okay, so what is being done here? We have a evacuated chamber. We have a chamber that is evacuated and connected to a pump to suck up all the air outside. Inside it is a vacuum. Now here we have a very fine source of alpha particles. Okay, very fine, say a wire coated with alpha emitter, so that we don't lose many alpha particles. Like we use a slit for light so that we get very fine collimated beam of light. Likewise here we are using a narrow source for a very collimated beam of alpha particles. And to take it complete that, we'll pass them through a very narrow slit, say A. So the source should be kept here. So alpha particles will escape. Just hold on, my network is a bit unstable. Just wait a bit. Yeah, nice. Oh, wait a minute. Now what we have here? Here we have a photographic plate. And we have kept the magnetic field such that it is at right angles to the direction of the alpha particles. Okay, so you can apply right hand rule, then you can see the deflection of the alpha particles. So if we do that, we'll see that the stream of alpha particles will traverse a semicircular path and they will meet at a point. Okay, can you see the screen? Is it clear to you or is it blurred?
Clear.
Clear. Okay, fine. So we can check the spot, we can measure, study them, and we can get the radius of the semicircular arc. Yeah, now it's better. So suppose radius of the track, you can call it, is suppose r. Fine. Mass of an alpha particle is say capital M. Its velocity, which we intend to find, its velocity is v charges u. Now tell me, what are the forces acting on this alpha particle in this process? What type of forces is the alpha particle experiencing? What types of forces?
The nuclear force, sir.
Nuclear force? No, no, no. It's a this experiment is done in the lab. It's way way outside the nucleus. Alpha particle has already left the nucleus. Okay, it is outside that. Think of normal particle.
Sir,
Why
the
is it
Coulombic force.
rotating? Coulombic force. Why is it rotating? I mean, why is this semicircular tracks are formed?
So because of the negative charge, sir.
Where is the negative charge? Think, think. Everything is given. If there is a negative charge, then it will attract it. But what is the reason that it is making a track like this?
So I don't know.
No, no, you know. Just see what is written. What is written here? What is written?
So magnetic
Yeah, magnetic
spectrogram.
spectrograph.
Magnetic
And
spectrogram.
so, who is making this particle rotate or make this track? Is it
Magnetic
the
forces.
exactly? So you have magnetic force. So there is no other. There's no negative charge in this. I haven't connected it to a battery. We have a magnetic force, right? So what is the expression of magnetic force? If I
Zero
take the
R.
modulus at least, Q into V cross, that is the magnetic force, right?
Yes, sir.
So VB sine theta, but here I have chosen the magnetic field such that it is at right angles to the direction of the outgoing alpha particles. And suppose it's along a direction in cap say. So if I take the modulus, it would be nothing but QV. So magnetic force is QV capital V. Got it?
Yes, sir.
Now tell me what kind of force does a particle experience in a rotational motion? Something that it will experience only if it is rotating or revolving.
Sir,
Rotational
centripetal
force,
force.
what kind of force? Very good.
Centripetal.
Centripetal, centrifugal, whatever. Yeah. I mean, expression is same, but the meaning is different. Yeah, very good. So, what is that force? Say the centripetal force. What is the expression of that force? It is m v square by r. I hope you remember this formula.
Yes, sir.
So now see, why is it rotating? Due to the magnetic field. That is, due to rotation, it is experiencing a centripetal force, which is nothing but the magnetic force. Therefore, we can write that QVB is nothing but mv square by r. So from here we can find the value of velocity v. It's qbr by m. It is very important, this formula. Okay, this is true for any particle, any charged particle in this magnetic spectrograph. Got it?
Yes, sir.
Are you able to see everything properly? Just tell me once again, because
Yes, sir.
it's very cloudy out here. The network is
Okay.
very prone to be bad. Okay, so for most natural alpha emitters, that is for maximum naturally occurring alpha emitting nuclei, this velocity is found to be of the range of the order of 7 to the power 10 meter per second. Fine. So this is how we can find the velocity of a alpha particle. Next is a very important concept in this regard called range of alpha particles. Okay, range of alpha particles. Do you remember range of a projectile?
Yes, sir. Not the formula.
No, not the formula, what it was. Formula is not required.
Yes,
What was range? I mean, what was the meaning of range? Acha, I don't remember, I think. So a very important property of alpha particle. See, once alpha particle enters in a medium, suppose it's not in vacuum, it is in any medium, gaseous medium, solid medium, liquid medium. What it does, it has the alpha particles. They have a very important ability. They can ionize the material through which it passes. What do you mean by ionization? What do I mean by ionizing?
So when a particle acquires a negative or a positive charge,
Yeah, how is it acquired?
so by losing or gaining
Yeah,
electrons.
exactly. So suppose this is an atom of the medium and this is an alpha particle. Alpha particles are actually very massive compared to beta and gamma particles. Gamma particle is massless, it's a photon only. Uh, so due to this massiveness, when it hits at a material atom, what happens? It can knock off the outermost electron from the atom. Hence, this atom now becomes a ion. So this is a very important property of alpha particles. So now what happens? Suppose you have projected alpha particles to a medium, say solid medium. So what will happen? It will go on ionizing, and with each ionization, what happens? It loses some of its kinetic energy, isn't it? Because whenever it is knocking out something, the energy is being lost to ionize that atom. So if I am losing kinetic energy, that means I am losing my velocity as well, right? Isn't it? The kinetic energy Ek is dependent on the velocity if mass is fixed, right? So what happens? The alpha particle will go on ionizing, and eventually its velocity will go on decreasing. Then it will stop moving and hence stop ionizing. It will, after a particular distance, it will cease to ionize. So the distance that it travels till that point is called range of the alpha particle in that medium. Is it clear what I'm telling?
Yes, sir.
So it is simply the distance that an alpha particle travels in a medium before it stops ionizing. So definitely range will depend on two things. First, the particle, that is the particle, when I say I characterize it by its velocity, energy, and secondly the medium. Obviously the range in the solids is expected to be lesser than that in fluids, right? Because of the compact arrangement of the constituents. Got it?
Yes, sir.
Now, how is this range actually dependent on the particle? That is the velocity of the particle rather. So this thing could be understood by a law which was uh, put forward by Geiger. GM counter you have studied, Geiger Muller counter. That same guy, that same person, Geiger. So it's called the Geiger Geiger's law. Geiger apostrophe S law, Geiger's law. So Geiger said that the range of an alpha particle is proportional to the cube of its velocity. Keep in mind, from now onwards, if nothing stated, then R will mean range of alpha particles. If I don't state otherwise, then R is the range of alpha particle. Now, obviously, not all alpha particles will have the same velocity. If all alpha particles of a uh, say beam of a group has same energy, then we call the alpha particles as monoenergetic alpha particles because velocity is proportional to energy. So if you make this an equation, you'll get a constant small a. Okay, R equals to a v cube. Now we also know that v and e are directly not directly proportional, but the relation is like kinetic energy is equals to half mv square. That is, we can say that energy is proportional to square of velocity. Hence, velocity is proportional, or the square root of energy is proportional to the velocity. If we insert these things here, then we would get the range in terms of energy as b e to the power 3 by 2. B is, you can understand that the constant should change due to the fact that I'm inserting 2m these things. Okay, so these two are the expressions of Geiger law. Now the typical range of uh, almost all naturally occurring alpha particles is between 5 to 10 MeV. That is the range of energy of alpha particles that we see being emitted. Okay, Ayush, now tell me what is the dimension of range?
So dimension of what, sir?
Range, range. Very simple. What is range? I mean, I'm asking what should be the unit of range?
So range is the distance covered, no?
Yeah, so I can express it in meters,
L,
right?
L,
M. So if I can
sir,
express range in
L.
terms of meter and L, right? Dimension of R is L, right? So in SI, if I SI system, if I express range in terms of meter and energy, I have already told you in nuclear physics the most acceptable and convenient unit is MeV, million electron volts. If we express range and energy in these units, and of course velocity in meter per second, then we will get A is equals to 9.416 into 10 to the power minus 24, and B would be 3.15 into 10 to the power minus 3. So these would be the values of the constants. Okay. Now there are other factors on which range depends. The most common uh, two factors common to physical factors are pressure and temperature. How do pressure and temperature affect the range of alpha particles. Now see, the range of alpha particles should be inversely proportional to the number of collisions, right? Isn't it?
Yes, sir.
If you collide more, what will happen? You will lose more energy and hence you will be able to traverse lesser distance.
Yes.
Now
Yes, sir.
tell me, how is pressure and collision related? If I increase pressure, what will happen? Will collision number increase or decrease?
The increase,
Why?
when you increase pressure, the space is less, so the number of collision is
Very good.
increases.
So you're getting lesser space, that is, the colliding particles are getting more closer. So the exact expression I am not aware, it's better not to write it like this. So better we can say that we can say we don't know whether it depends on 1 by p square or p cube. So we'll say that range decreases with increase in pressure. Now tell me how, what do you expect with temperature? I mean, how temperature affect range?
The temperature also decreases the range, sir.
Why?
Because increase in temperature causes the particle to, so the collision increases when we increase the temperature. That's why.
Pollution increases. Acha, okay. Now, but if that is also correct. Hmm. But it is found that range increases with increasing temperature. Okay, increasing temperature. Now try to explain this. What you're telling, that is correct. If I increase temperature, there would be more random motion of the of the gas particles. Hence, the collision would be more. But I think the reason is that this. No range. Okay, I'll see this. Okay, once again, I'll just check whether it is correct or not. Maybe the gas molecules are now moving far away from each other. That is giving more, mean free path. But what you're telling, that is also correct. Okay, acha, I'll check this thing. So this formula given by Geiger, R equals to A V cube or B e to the power 3 by 2. It's an empirical formula based on experimental results. Now we can deduce this formula as well mathematically. Before that, we need to know one more thing, that is called specific ionization. So what does it say? So what we have, that what ionization does, ionization creates large number of ion pairs. Okay, ion pairs are generated along the path through which the alpha particle will travel. Okay, so in a gas, what happens? This ionization would be seen to be creating ion pairs along the path of the alpha particle. So the number of ion pairs which is formed per unit path length at any point along the path of the alpha particle, that is called the specific ionization. That means suppose uh, this way, this is the density of the gas molecules. The alpha particle goes this way, the ionization that it will do, and if it goes this way, obviously this way the ionization will be less because number of particles gas molecules is less here. So what specific ionization will tell, it will tell us simply that how many ion pairs or how many you can say uh, ionizations have occurred in unit length along a particular direction. Simply it is nothing but DE dr along unit length of range, how many ionizations have taken place. And we know that E is proportional to R to the power 2/3. If R is proportional to E to the power 3/2, E will be proportional to R to the power 2/3. So this thing would be proportional to R to the power minus 1 by 3. And we know that R is proportional to V cube. So again, V is proportional to R to the power 1/3. So this thing is proportional to V to the power minus 1, that is 1 by V. Okay, actually this there should be a negative sign. D is actually it takes care of the energy lost. Energy lost in collisions. That is, it will tell us that how much energy will the alpha particle lose along a particular direction. And now see if the energy of the alpha particle is getting lesser, obviously the more the V, less will be the decrease in energy, right? If it is more energetic, the decrease in energy would be lesser. So with this we can try to prove the Geiger law. Let's try to prove it. Proof of Geiger law. So what we got, the thing that we got is specific ionization. So let me write it like this: minus dE dx, which is proportional to 1 by V. Why is the minus sign? Minus sign is for decreasing energy. X is the distance. So I can do one thing, I can keep a constant of proportionality, say K. So K is a constant which will depend on the absorbing medium. Okay, got it?
Yes, sir.
Okay. Now, if we take the non-relativistic case of alpha particles, that is simply if we can write that E equals to half mv square, because you have studied in relativity that this is a special case. Actually, if we take the relativistic case, then there would be many terms occurring here, and the first term is half mv square. Other terms are like v by v to the power 4 by c square kind of 3 by 8 something, and we neglect them. So this is the case. Then what we can find if we do the differentiation here, because here we have E and V also. Let us substitute one in terms of other. So we would get mv dv. So now what we get from this equation, we will get minus, instead of d I can write mv dv dx is equals to k by v. So dx should be equals to minus m by k v square dv. Dx m by k v square. Is it okay? Just check it yourself.
Yes, sir.
Now let's integrate. So let us integrate dx, and here I have minus m by k v square dv. Now the limits are important. So what is the limit? So initially the velocity of the alpha particle was v when it didn't travel any distance. Once it has traveled its range, it will come to rest. So for dx the limit is from 0 to r, and for v it is v to 0. Put them, what you will get is r is equals to m by 3k v cube. So m by 3k is a constant. So r is equals to a v cube. That is the Geiger law. Now the network got good.
Yes, sir.
Okay, and there is another law. This will be the last thing we discuss today. That is regarding the uh, decay constant of the alpha emitter. It's the Geiger-Nuttall law. Geiger-Nuttall law. So the decay constant lambda is related with the range as ln lambda equals to a plus b ln r. Now a and b are constants which differ radioactive series. That is whether your series is thorium, uranium, actinium, neptunium, whatever series it is. According to that, these constants will vary. And if you try to write it in terms of energy, which we can always do, and here since we have ln, so the power will come as the coefficient, but that will change the constants. So in terms of energy of the alpha particle, it looks like this. Okay, these are the two forms of Geiger-Nuttall law. So very important formulae these are. In the exam, suppose you are given only the range, from there you can find, or you can write the expression of ln. Sorry, not ln. I mean Decay constant. You can draw the graph also. You can see it would be a linear graph. So the graph looks like this. It's y equal to mx plus c kind of graph. So if you plot ln lambda this way, and if you plot ln r, so it would be like straight lines. But for different series, you would get different lines. At different points, there the elements or nuclei which we get by decaying. So the first one would be the uranium series. Second would be the thorium series. And the actinium series. These are the three natural radioactive series. Okay.
Yes, sir.
So I think that's all. So we have class again on Thursday. So on Thursday we'll discuss more.
Yes, sir.
Fine. Next we have a straggling of range, then alpha disintegration energy, etc. Okay. Okay. So if you have any problem, you can ask. Any doubt?
No doubt, sir.
Okay. Take care then. We'll meet again on Thursday.
Thank you, sir.
Okay. Thank you.